All right. Well, sorry for the delay, everybody, but welcome to the Planetary Science Sample Seminar Series. The first one of the semester. So, please give us
all employees can be reporting in person too.
Director and a professor here at the University of New Mexico, the director of the Institute of Meteoritics. He teaches courses on igneous petrology, mineralogy, the solar system, and the planet Mars. Dr. Agee's research focuses on meteorites, in particular meteorites from Mars, a contrast from the early solar system, and on the origin and evolution of planetary interiors. Before coming to New Mexico, Dr. Agee was the chief scientist for astromaterials in the office of the director at NASA Johnson Space Center from 1998 to 2002. And then from 1990 to 1998, he was on the faculty of the Department of Earth and Planetary Sciences at Harvard University and was a visiting scientist from 1988 to 1990 at the University of Bayreuth in Germany. He is a fellow of the American Geophysical Union and the Meteoritical Society of the Meteorological Society of America, and is an F.W. Clark Medalist of the Geochemical Society. Dr. Agee holds a bachelor's degree in geology from the University of California, Berkeley, and a PhD in geological sciences from Columbia University. And I have talked enough for now, so
I'm impressed.
Carl, please take over.
I'm totally impressed with your reading and verbal skills. That was a very nice introduction. You read verbatim what I gave you. so that all is it's all good. Yeah. So sorry for the delay, folks. I'm going to talk today about some new unique meteorites from Mars. Here they are in the first slide. It's Northwest Africa 16272, Hassi El Madani 002, and Tagaza 001. So let's just launch into this. And so let's start off first with NWA 16272, which is I classified this meteorite as a Martian vesicular basalt. That's a new unique type of Martian meteorite. And it was reportedly found in the Algerian Sahara in 2022. The entire sample consists of one stone. You see it in these pictures here. These are photos that I took. I had the stone to work with from the finder, from the owner, and it weighed 202.2 grams. And the meteorite hunter/dealer in Algeria told me at the time that he thought that this was a new angrite, an angrite that was found near a previous angrite find. And that previous angrite was one that I classified for him. And so when he said, oh, I've got another piece of an angrite, I'll send it to you. And it looks really interesting. And so I got the sample, and the first thing that I did with the sample, well, first of all, that angrite that I classified and that he had provided is called Oed Mamos 001. It's a volcanic angrite. You can see that it has bugs, it has phenocrysts, it has ground mass. It was found in Algeria, as I said, previously in 2021. Okay, so this sample that we're going to talk about today is NWA 16272, is definitely not a volcanic angrite. The first thing that I did with this meteorite, which it's usually the first thing I do with any unknown sample that I get to classify, is that I put it on the electron probe. Mike Spildy actually does that. and we do a bunch of pyroxene analyses. And we plot those pyroxene analyses up on a plot like this one, where we have iron and manganese plotted against each other in atomic formula units. And you can see all of the yellow dots there are the data from the pyroxenes in this meteorite. These pyroxene iron-manganese ratios are 34 plus or minus 4 from 63 analyses. These are Martian basalt values. These are definitely not angrite values. Angrite values should be up around 70, okay? So that was the first thing that popped out of this, and it was like, wow, this is not an angrite at all. And this is like, if this is a Martian meteorite, this is something quite different. And indeed, it turned out to be something quite different. I gave the sample to Karen Ziegler because, after all, that's what I do when I'm posed with an interesting puzzle and I haven't quite figured out what this is. We do the oxygen isotopes. Karen analyzed 12 bulk analyses did total bulk analyses doing laser ablation, laser fluorination, oxygen isotopes on these bulk sample fragments. And she came back with a value of for cap delta 17 of 0.58 plus or minus 0.04 per mil. These oxygen isotopes are nearly identical to the Martian polymicrechia NWA 7034, aka Black Beauty, which has, again, almost identical values, and they're plotted on this oxygen isotope diagram of small delta 17 oxygen versus delta 18 oxygen. And you can see the array of Martians, SNCs, that is, in red. The turquoise are Black Beauty, NWA 7034, and you can see that the yellows, NWA 16272, plot right on top of Black Beauty. So this is very exciting. This is actually the only other meteorite that I know of that plots in exactly the same place as Black Beauty. So this is, again, super exciting. And and again, we took those pyroxene analyses. I plotted them up on a quadrilateral diagram for pyroxenes, and just to compare them with Black Beauty, they're quite different. This is not a piece of Black Beauty. Don't want to make it sound confusing. This is a different rock altogether. The yellows show that there is a really strong igneous crystal fractionation trend, starting with pyroxenes, low in calcium on the left, and then spanning all the way out to ferro-pigeonite, ferro-subcalcic augite compositions. Black Beauty, on the other hand, has two populations, a sort of an augite, magnesian augite population, and then a population actually that has within it sort of some of the trends that we see in NWA 16272. So they're not the same, and we can see that also in the rare earth element diagram, where we have Black Beauty at the top, whole rock analyses, and NWA 16272 below it. They both have negative slopes, which is not common in Martian meteorites. None of the sugartites have that. Some of the knocklights have those negative sloping trends. Both of these samples, both of these rocks have europium anomalies. Black Beauty has a negative, and NWA 16272 has a mild positive europium anomaly. Okay, and so then just to compare NWA 16272 with other Martian meteorites and Martian samples observed from rovers on Mars, here we have it plotted on a total alkalis versus silica diagram for volcanic rocks. And you can see that the yellow star shows that NWA 16272 plots sort of up in the more alkali-rich portion of the SNC meteorites, but it is not as alkali-rich as the bulk Black Beauty composition is. Okay, so I just wanted to again reiterate the textural uniqueness of this meteorite. You saw it in those pictures, the amazing large vesicles and bugs and so forth. And of course, that is not uncommon in volcanic rocks. We see this, of course, on Earth, but we also see it on Mars. Here's a view of the Martian surface taken from the Perseverance rover. And you can see that there are indeed some vesicular basalts here exposed on the surface in the maze formation. Here is an older image here are older images from the Spirit rover at Gusev Crater. And again, there were vesicular Martian basalts there as well. It's just that, when you look at the collection of Martian meteorites, we don't see any of these very fragile vesicular basalts. And that makes a lot of sense because they're They're easily broken up. They're probably it's harder for them to survive launch off of Mars and an impact, and then make it through the Earth's atmosphere intact as well. So it's not surprising that these are unusual in a meteorite collection, even though they're ubiquitous and abundant on terrestrial-like planets that have basaltic volcanism. And of course, let's not forget the moon. The moon has many examples, especially from the Apollo 15 landing site of vesicular basalts. Here are just some nice
or something.
that could be.
Because, I mean, it doesn't, even a vesicular basalt is pretty tough. I can't imagine that that would not be able to fall through the atmosphere.
True, true. Yeah, I think the other thing is that they're not well preserved also once they get on Earth. So once they sit on, I mean, if you have a fresh one, that would be fine. But if you have a, let's say, a vesicular basalt that sits out in the Sahara for 1,000 years, it's going to be more easily, because the thing is full of holes. And it's got a lot of surface area, so it will tend to degrade quicker. And we see this also.
The vesicular basalts are way older than 1,000 years. They're still pretty darn fresh.
They are. They are.
So,
They are.
I'm
So it's
wondering
in,
if it's not something about the
Yeah.
near the surface
it's
and an impact just blasts that
Yeah.
stuff to bits.
absolutely, and it's very interesting. All of these things are very interesting about, because we see a lot heavy shock that's in most Martian meteorites, especially the Shergottites. Not so much the Chassignites, Knocklites, but we see that a lot of the mascalinite in those indicate a heavy shock and lots of fragmentation. This meteorite, for example, has no mascalinite, and Black Beauty doesn't either. For example, all the plagioclase is crystalline. So these are examples of ejecta from Mars that are that did not experience the intense shock pressures. They could be distal, okay, from the crater or from the impact, and that they're still lofted along with the rest of the material.
So if there's volatiles underneath, that would help eject them.
Possibly, yeah.
Can I ask one more thing?
Yeah, of course.
You had a plot of showed that this sample is similar to the normal basaltic rocks of Mars there, and that Black Beauty is much higher in the alkalis.
Yeah,
And yet the isotope composition is not typical for the mantle-like composition. Did you separate say olivine and measure just those grains?
yeah. Well,
Because I
I'll
would
get to
predict
that.
that those are
Karen did try to do that, but we had another goal in mind. I'll get to that at the end of this section, and hopefully that'll be clear. But the Black Beauty, that cross with the turquoise dot, that's a little misleading because Black Beauty actually is polymicrotria, so it has actually an array of compositions that span quite a large range on this diagram. So that's a little misleading. This sample on the other hand is not polymixed at all, and so that composition is pretty tight for this guy. So this is one of the first early slides that Mike Spilkey made for using the SEM, and you can see the meteorite is primarily a fine-grained quench basalt, okay, but there are phenocrysts within it, and there are also these bugs all over the place. And some of the bugs are chock full of desert sand. And in fact, you can see that in the upper right. That bug there is completely packed in with little grains of quartz. And those are not quartz grains from Mars, those are quartz grains from Algeria, okay? And so, but we saw some very interesting, so the ground mass is, and it's made up of plagioclase and pyroxene, olivine absent. This is what I'm calling the host, or the main composition that we're looking at. But there are contaminants from the Earth, and I think there are also xenocrysts in this meteorite as well. And some of the large crystals, the so-called phenocrysts that we saw in here, they have almost all of them have resorbed rims. They all look like they're unhappy in that background. For example, this pyroxene looks very rounded, very no faceted surfaces. The plagioclases are maybe not as easy to see in this particular slide, but it could be that the pyroxenes and the large crystals that we're seeing in here are actually, in fact, xenocrystic. Okay, and then we did, Jim Garvin arranged some nice,
XCT.
Yeah, XCT. This is one of the first ones he did. He did actually a bunch of really good ones, but I just loaded this one because it just shows really quickly for presentation purposes what the vesicular nature just sits through the whole thing, right? And you can also see some of the phenocrysts that are sitting in there.
And there's those xenocrysts or phenocrysts, they look rounded.
I think they're xenocrysts. I think there's, so that's a big enigma. That's something that's very unusual and hard to understand. And I'm getting to the end of this part of the talk because I've got two more meteorites that I want to discuss. So this is, I could have devoted the whole talk to this one, but I wanted to mix it up a little. So Karen and I were very excited about the fact that there's all this orange stuff in this meteorite. And we're like, this does not look like desert weathering. You know, we've seen desert weathering in meteorites all the time. And this stuff is just so weird. I mean, it's so orangey and so who knows? I mean, that's, you know, sort of a qualitative term, obviously here. But so we're excited about testing to see whether this is, and these are low total regions. They're basically iron hydroxides and other alteration products that are probably hydrous. And so we were interested in searching for, well, determining whether or not these alteration components are terrestrial or Martian. And in doing so, I mean, Karen did like 60 analyses of individual grains, and this is the typical, this lower panel just shows a typical crushed piece, and then she would go in and grab little pieces and do each individual one. And she did like 60 of them, you know, and they're not all on this diagram because some of them were quartz grains, and they plotted way up in the upper right-hand corner, way off the diagram. In doing so, we found no evidence for Martian oxygen isotopes in the alteration material. That doesn't necessarily mean that they're not from Mars. It could be mixed in with terrestrial contaminants. Again, this is a meteorite that sat in the Sahara Desert for a long time, perhaps. So the jury's still out on that. But the weird thing is that as she was doing this, she would find occasionally some pieces that looked like pyroxenes and looked like feldspars. We didn't analyze them with a microscope, but we did do oxygen on them, and they all plotted below the terrestrial fractionation line. Some of them plot down by the HEDs and the angrites, and then there's this population of purple ones that sit below the TFL. Those look sort of like feldspars, but again, we don't know exactly what they are. In any case, these look actually like extraterrestrial xenocrysts. So and within the within the matrix that is actually identical to NWA 7B34. So there are sort of three components in this meteorite in terms of oxygen isotopes. There's what I call the host, which is identical to Black Beauty and oxygen. Then there are the terrestrial contaminants that are really obvious that you can see, and you can spot them also as being quartz grains and so on. And then there's another population. Looks like these are xenocrysts that are extraterrestrial. So this is a big mystery, and it's something that we still haven't fully explained to our own satisfaction. I'm going to stop there with slides and just summarize the current and future work on this one. So right now we are I'm collaborating with groups at ETH, Chicago and Berkeley. They're doing noble gas, in situ strontium isotopes, and argon dating. Those data are in progress. I just want to say the noble gases, though, so far, what I've been hearing from Interbicimen is that they are consistent with Martian atmosphere. So that is very exciting. Further, we need to understand, is there a connection to Black Beauty or not? Is it just coincidental that the oxygen isotopes are the same? And then it also starts to open up the question of how diverse are Martian rocks. That's a whole interesting problem unto itself. We also have to have a scenario that can help us understand the so-called non-Martian oxygen isotopes, Xenocris and Xenoliths. And we would like to continue our search with maybe more sophisticated means to determine whether any of the alteration products are Martian. And then back to what Zach was pointing out a minute ago about scenarios for survival of launched vesicular basalt and other Martian materials and their preservation as meteorites. Okay, so on to the next meteorite. The next meteorite is, its name is Hassi el-Madani 002. Hassi el-Madani 002 was reportedly found in a hamlet in Algeria, outside of a hamlet in Algeria in 2022, also the same time frame. And this is a 465 gram meteorite, a bit bigger. And it has two different lithologies in it. You can see these in the picture. This thing, especially the so-called light lithology that I've made an ellipse around, caught my eye immediately. And I'm like, what is this? So it turns out that this light lithology makes up maybe about 15% of the total stone. So we sampled both of these before I do that, I just want to show you one of Jim Garvin's movies that they made at Goddard, and this is, the colors are quite different from the real one, but these are backscatter, equivalent to backscatter, I think. But you can see the two different lithologies quite distinctly. There's this background it's got a lot of dark and light grains in it, and then there is this inclusion or nodule that shows up here as dark, but actually in visible light, it's the light part. So it's a little counterintuitive perhaps, but here you can see it. And looks like there's also a reaction rim around the nodule. But these are look like two different meteorites. It's not unheard of in meteorites because there are lots of pressures and so forth. I'm not going to show this whole movie. I'm going to just move along because we have some more pictures here. But this is a summary of what we just saw. So the light lithology is I've outlined. Looks dark and backscatter, but it's the light part that caught my eye. And we actually, you can see here already that little embayment there next to the label light lithology. That's actually where I took a piece of sample out. I chipped it out, just took a chisel and chipped it out. We didn't do any cutting initially. I tried to take as little material so as not to spoil it. And these are the pieces. So the one on the left is a couple pieces of the light lithology. You can see it's very white, it's sort of tan grains. And then the dark is very dark. It almost looks like a dark, shock darkened composition or something. So anyway, I gave the sample to Karen again. Tell me what this is. And the light lithology came back plotting in the Mars SNC array. Okay, so very exciting. I thought, great, I've got a polymorphic breccia from Mars. So I was really excited. We're going to have two. So that I can't wait to see what that dark lithology is. It's another piece of Mars. And so when Karen showed me that data, it was surprising because the dark lithology is not plotting with the SNCs at all. Way off up in the upper right-hand corner of this diagram. Guess what it corresponds to? Corresponds to LL chondrites. So that host, the 85% of that meteorite, has affinity to LL chondrites, and it turns out to be the case from them looking at the major and trace elements of it as well, although it has no chondrules. So it looks like it might be like an LL7 or an LL primitive achondrite, something like that. But it is definitely not plotting with the light lithology in the Mars SNC meteorite array. This just shows you again how important it is to have oxygen isotopes. Okay. And so this is the light lithology BSE, 100 micron scale bar in the bottom. It turns out this is a Martian troctolite, at least if it's from Mars. Okay. I believe that it is, but again, it's so different that we'll see what happens in the next year or two as we study this further. But it's the first Martian troctolite, At first I thought this was a dunite, but it actually doesn't have enough olivine to qualify as a dunite. It's got about 75% olivine. The dark gray in there is mostly mascalinite. There's about 20% mascalinite, so that makes it a troctolite instead of a dunite. It fits, but it's not identical. And chromites, they're ubiquitous. That's common in Martian dunites, like chasignite, for example. And so I plotted these up on an old ternary diagram for classifications. HEM is Hassel-Madani 002, the light. You can see it plots near the chasignites. They're all sort of in that corner down by olivine. And in fact, here are the 3 known chasignites. There's NWA 8694, which is a peridotite wurlite. And then chasignite is actually a true dunite, and NWA 2737 is a true dunite. It's all as well. But you can see they're all clustered down in the corner near olivine, and HEM 002 is in the vicinity, but at first I was saying, oh, this is the 4th chasignite, but actually it's not a true chasignite in that regard. On the other hand, NWA 8694 is also not a true chasignite if you think a chasignite has to be a dunite. So anyway, maybe that's splitting hairs, but that's what I came up with. So what is going on here? There are many possible explanations, I'm sure, but it occurred to me that if this is a piece of Mars that's embedded into an LL chondrite or having an LL chondrite precursor, that somehow there has to be a Martian connection to this. And so how do you get LL chondrite mixed up with Mars? You have to be in the vicinity of Mars, perhaps. And so one hypothesis would be that Hassel-Madani 002 is derived from the same giant impact orbital debris, a mixture of Mars and LL that formed Phobos and or Deimos. So again, it may be related to the Martian moon formation. It may not be. There may be other better hypotheses, but this is one that I came up with that put it in the neighborhood of Mars, but not on the Martian surface. Maybe there is an LL chondrite on Mars, on the surface somehow that got mixed in with. Anyway, you get the idea. There are a bunch of different possibilities, but this is actually testable. How is it testable? Well, it's testable because there's actually a mission that's going to go to Martian moons. It's called MMX mission. It's a Japanese mission. It's the folks, and it will test the hypotheses about whether the Martian moons are in fact a pair of asteroids captured after the formation of Mars, or B, the moons are fragments that scattered during a giant collision, a giant impact with Mars that then coalesced. The option B would be consistent with Hassel-Madani 002. And again, so this is something that could be tested down the road to see what it indeed is. And I think they're going to do a sample return from this. So they'll actually have pieces of Phobos, and we can see if there are chunks of Mars mixed in with Phobos. This is the final deposit sample that we got out of this sample. I got those little fragments chipped out, but the owner generously sliced a really nice piece right out of that captured that nodule. You can see it up there in the upper right-hand corner of that slice. We have that in our collection now. And then in the meantime, the team at Lawrence Livermore is doing more work on this, doing isotopes on this. And Thomas Cryer has a LPSC talk talking about the isotopic constraints on the origin of this differentiated achondrite that I think is from Mars. And so stay tuned for that. All right, so now we're going to wrap it up with, hope I have enough time still. You're doing okay?
Oh yeah, you got plenty.
We got started a little late.
Yeah, no, you're doing.
Yeah. And so this is called CASA 001. And this is just a sneak preview. This is like the trailer, right? When you want to go see a movie, because I'm not going to give the punchline. The punchline is coming. It's forthcoming. But I've been sworn to secrecy about this. So anyway, CASA 001 is a pyroxene ferric sugartype. It consists of a bunch of stones that were found together, nearly 800 grams. So there's lots of this material in contrast to the 2 previous meteorites I was just talking about. This Martian meteorite was found, again, 2022. 2022 was a good year for finding weird Martians in North Africa. This one was found north of the archaeological area of Tagaza in Mali, which is in the Sahara. A lot of people don't know that, but it is also in the Sahara. And it was found by Sawari meteorite hunters. Those are the nomads that live out in that area. And the find locality is, again, here, there's some information about that, but basically it ended up that there were 8 identically appearing stones that were found in this locality. And the largest stone that's sitting on that balance is 442 grams. I classified this as a pyroxene ferric shergotite, i.e. not having olivine present, mostly pyroxene plagioclase, and I based that initial classification on the iron manganese of the pyroxenes and the anorthite content of the mescalinite. And then when I gave it to Karen came back and gave us something different. And I'm like, wow, what is this? And so the CASA data on this oxygen isotope plot are the yellows. Above the yellows are Black Beauty, and to the left down is the SNC array, and the TFL, terrestrial fractionation line, is the blue line. The delta 17 values are right on the money for Mars, but the delta 18 values are anomalously high. I still think it's Martian. And from looking at all of the other geochemical parameters, but something has affected this meteorite to make it have different oxygen isotopes from the SNCs, because it really looks like a shergotite. Okay, this is if nothing else, the take-home message from this talk is oxygen isotopes matter. Okay, yeah, and so the other thing that caught my attention as I was looking through this meteorite, of course, we always go to the pyroxenes first, look at them. And these pyroxenes look really crummy. They're full of all of these alteration cores, the cores of them, not the rings, but the cores are like turning into something else. And this is, the one on the left is actually just a reflected light photomicrograph, just done with a microscope, picture taken. And you can see that dark core of that pyroxene grain. And then, so now I'm working with Yang Liu at JPL on this meteorite, because I found that that altered area was rich in manganese. And I'm like, manganese and Mars, who knows about this? And I thought, Yang Liu knows about this. So I said, hey, you want to look at this meteorite? And so she did, and we're working on this together now. And this is a better image that she did. And again, she confirmed there are manganese-rich areas with chlorine and phosphorus. And then the thin lines are an iron hydrated cluster. And so that in itself is already interesting. But she's been going through this meteorite with a fine-tooth comb, and sure enough, there are zircons everywhere in this meteorite. And here, this is just one image that I pulled up. I think there are a bunch more that we have, but anyway, there are zircons all over the place in this meteorite. And they've done lead and uranium lead dating these. And we have ages for Tagaza 001. But I'm sworn to secrecy about what the age is. But I can guarantee you the answer is exciting. So there is going to be a paper with the first author, Yang Liu, and Carl Agee somewhere trailing it towards the end, the list of people who worked on this meteorite. And we're going to submit this for publication, of course, very soon. But a lot of the work on this was delayed because we were going to have a meeting on the same day that the LA fire started. And a lot of people in Pasadena and Altadena and some of her colleagues lost their homes and things like that. So that's come to us. This collaboration is a little bit on hold right now, but I'm really excited about this. This is going to be something, it's going to be an interesting contribution to what we know about Martian meteorites. That's it. And so I have a short talk. I could have made this a lot longer, but it's a good thing I didn't because we started late.
That's a pro.
But we can, here are the three that I talked about: NWA 16272, vesicular basalt, Asi El Madani, we call this affectionately Phobos, and then Tagaza 001 is this new meteorite that we have an age on, but we're not going to tell you what it is yet. Okay, thanks very much.
Okay, and then we'll go ahead and open the floor up to questions if anybody has any questions for Carl. So,
While you're looking online, let me just ask if
Yeah,
the
go ahead.
oxygen isotope composition, delta 18 being heavier, could just be explained by difference in the bulk composition of the rock. It's more silicious and therefore should be heavier.
Good point. Good point.
Okay.
Yeah, I didn't know. I didn't realize that. Yeah.
I mean, a rhyolite's up at 9, on Earth,
Yeah.
whereas
Okay.
a basalt is 5.5.
Yeah, I attribute it to the alteration.
Yeah, so you can figure that out
Yeah.
based on the abundance of the different
Yeah.
minerals.
But there was something different about this one, for sure. Yeah.
Any ideas how or why the pyroxene would be altering from the inside out
No.
instead of these?
Well, we saw this in another Martian meteorite. Sultan Bachi worked on one, but these were olivines, and the cores were rotten, and the rims were beautiful. And then he went up to Colorado and found some terrestrial basalts that had similar alterations. I don't think it's desert weather. I think it's some sort of hydrothermal thing. But why the cores? Well, if the cores maybe, it's kind of weird, because the core should be magnesium rich,
Yeah.
and the rim should be iron rich.
Yeah.
And this magnesium pyroxene alter quicker than iron pyroxene? I don't know. But it's such a counterintuitive thing. You would think that if it's being altered from external, sources, that the rims would be the things that would go first. And the cores would maintain the pistonality, whatever the word is. And but these are the opposite. So, but we've seen it again in Martian meteorites. But this one has got, almost every single cluster of pyroxenes, you see one of these cores. Yeah.
One more.
Okay.
So it's really interesting that one of those rocks has what appears to be an LL chondrite fragment in it, but that's intriguing because most impact melt ratios don't have 100% components of the impactor. It's some mixture of the two. So it's really curious that it appears to be a holistic LL chondrite-like component, despite the fact that that's rare in impact melt ratios. So
what would you expect it to be?
a mixture of a Martian and the LL chondrite.
Well, yeah, but this is only, this is less than a half a kilogram. So who knows with the huge piece.
That they should be physically alive.
Yeah, it's really unusual for it to have a largely intact.
Oh, yeah.
Yeah.
Well, what we were looking for in the scans were evidence for more class in the Martian, and we don't think we found any yet.
Yeah.
But we have, from the same person we got this meteorite from, he said, I got another one that's also a little thing like this. And so we actually have about 6 of these. They're all much smaller than this one.
Yeah.
And the trouble is, you chip it out and then it's gone. So what we're doing now is we're slicing through these basically little chondrites.
Yeah.
To try to expose potential chondrite, this Martian mythology. So far we haven't been successful in doing so, but it's different.
Yeah.
But again, you have to worry about always when you're looking at meteorites. You get sort of carried away sometimes by the fact that you have a microprobe and a microscope delving down into this thing, and then in reality, in the physical world, it's just a little tiny rock, right?
Yeah.
And so who knows what else is there?
Maybe instead of the impact, it's post-impact in the cloud around
In the cloud.
Mars where these
Things
things
accreted together. Yeah.
well, Carl, we have a question from the chat from Ching Zhu asking, other than oxygen isotopes, are there any visible chondrules in the LL chondrite?
So far, we haven't seen any. but there's there's metal and there's metal present at sort of LL levels. Not a lot of metal, but there's also there's a typical olivine, pyroxene, and plagioclase that you would expect. So it's like an LL7, no chondrules present, or maybe an LL primitive achondrite.
And then Justin made the comment that it's rare to have distinct components in a rock like this. I think that's Tony what you were.
Yeah. It's very unusual. That's why I was expecting the dark lithology to also be Martian.
Mm-hmm.
So I was super surprised when I saw that it was a chondrite, because I was kind of disappointed. I thought, oh, we got a shock darkened chasignite and a piece that's light that hasn't been shock darkened, but that wasn't what it ended up being, as the oxygen isotopes clearly demonstrate. It's something, two totally different things from two completely different parent bodies.
What was the modal metal content in that rock?
Low, quite low, and that's also common in a lot of these high grade, like the sevens and the primitives. They've lost. Some of them have lost the metal from partial melting and stuff. Yeah, but LLs are low anyway. They don't have a lot of free metal anyway. So.
Well, Carl, we have another question from Luigi, who is intrigued about the Hassi Amadani and is wondering if the contact between the Martian meteorite and the LL chondrite looks warm, and if not hot.
Oh, we haven't done a lot of work on the boundary layer, and that's one of the things we need to do. We did some I think Mike Spildy may have done a few cursory examinations of that zone. It looks like it's almost like a transition zone. You can see it in that one image from the CAT scan, the CT scan, where it looks like it's got like a reaction rim between the host and the nodule itself. So.
And then Ying Lu was asking, why is the oxygen isotopes of the troctolite higher than typical chassignites?
Why is there? Oh, well, it plots within the Mars SNC array. It's just on the high side of that array.
Okay.
But there's actually, some people have proposed that the SNC array in oxygen isotope space is a very tight array, and I don't believe that it is. I think there's a fair amount of variation from one SNC to the other. But if you do, let's say, pieces of a chasignite, various fragments, looking at fragments, not bulk, just fragments, you'll find that there is also a spread even within a single meteorite, Martian meteorite. So that SNC array is sort of like a linear cloud rather than a tight line. Yeah.
Okay. And then Justin was asking about if the LL hit a Martian surface target, like a volcanic lava flow, wouldn't it fragment? Would it maybe it would partially molten as well?
Yeah. So the question is, where did this come together? Did it come together on Mars,
right,
or did it come together in Mars orbit? And so I don't know the answer. It's just a hypothesis at this point, one that's kind of out there. But question is, what makes more sense? Does it get mingled together during impact, or does it get mingled together during the assembly of the Martian moon, if that's actually what happened?
I see. Okay. Do we have, I guess Arya is asking, would you expect a transition between oxygen isotope groupings in the boundary of the LLL/Martian contact?
Would be very interesting to look at. We have not done that. A lot of these would benefit from in situ measurements. Really, that's going back to those alteration products in the first meteorite, the vesicular. Again, it would be ideal to do in situ oxygen. We do grain separations, but basically when you laser them, they're gone, and so you sort of have to analyze them first, the microprobe, and then somehow do oxygen on them, or so in situ measurements would be of the stuff that we're interested in here. Yeah.
And also, thank you, Tony, for answering some of these questions in the chat. We're slowly getting to them. Do we have any other questions, comments before we head out for the day? Okay, well then, if that pretty much wraps everything up, real quick before we go, I do want to remind everyone, also, again, apologize for a little bit of a late going, but next week we have James Keene from Jet Propulsion Laboratory, who will be talking about Endurance, a potential sample return mission from the South Pole Aitken Basin. So please look forward to that. Everyone have a wonderful rest of your day, rest of your week. Thank you guys so much for joining us. And Carl, once again, thank you so much for the talk.
My pleasure. Thanks, everybody.